Hello, everybody, and welcome to season 5 of the Hyperthesis podcast. We are very excited to be back after our extended break to do some research, visit some conferences, and do a whole bunch of other stuff with our lives. But we are very happy to be back for episode number 57, where we'll be talking about everything from quantum Nobel Prizes to Bell's theorem and beyond. So, hi, I'm Patrick.
I'm Feely.
And I'm Liam.
Well, we are again excited to be back for this episode. It has been quite a while since we've released an episode, and we've had some mishaps trying to get things recorded, including some broken computers. But we are back, we are recording, and we have some fun updates. So before we get into some intro topics that we've prepared, what has everyone been up to in the break?
Well, I guess it's pretty normal when the semester starts in September, where we got to, settle into new semester. We do a bunch of trainings for maybe our teaching assistantship and stuff, and try to figure out the projects and where you are in your school year and academically, And it took some time to settle in with the new students, but I think everything is going smoothly. On research wise, I think I'm starting on kind of new-ish topic, which I think now we're at a very good pace. So it's good to do that. It feels good. I've been traveling quite a bit. I hosted a Thanksgiving dinner for around 9 people. That was good. Liam was here with us, and it was been pretty good so far this year.
I posted a photo of you and the turkey to our podcast Instagram. I don't know why. I just felt like doing it.
Yeah, it was the 14-pound turkey, some herb butter, and some other side dishes, and I think we had a good time. I think.
Yeah, we had some good food and some good philosophical, science-y conversations as per usual at Feely's household.
Sounds delicious, no matter how you look at it.
Yes. It's been so long since we last recorded that it's all kind of a blur to me. I don't know what's changed since then, honestly. I guess what Feely said, like we've started the new semester, even though it's almost half over now. But yeah, I'm TAing a first year introductory physics lab right now. So, I run this lab where you go in and they swing a ball on a string and it's a pendulum, and they can measure gravity, and they do all these kind of elementary but neat little experiments to learn how labs work and all that. So that's been fun. And I'm TAing a second year physics class on electromagnetism and circuits. So I haven't taken a circuits course since like 2016. Yeah, 2016 or 17, something like that. I mean, a lot of it, like I remember actually somehow. So it's actually been really fun to TA that class. We did like a voltage divider lab. That was kind of cool. Yeah, and I'm learning a lot about the hydrodynamical analogy for circuits, which is something that I don't think I was ever taught. But the guy who runs, like the head lab instructor for the second year class, well, I don't know what his official title is, I forget, but he really likes this hydrodynamical analogy between circuits and fluid mechanics. So I've been learning about that a bit, and I probably want to talk about it one day. But anyway, that's kind of like my quick update. My research is going good. I'm doing all this new fun stuff, and it's going pretty smoothly. I'll talk about it another time some more.
And in the meantime, I've been also busy. I was working with the federal government over the summer as part of the Canadian Forestry Service. So I ended that work experience program. Started this semester, of course, and I'm TAing as well, and a course on advanced remote sensing, which is pretty good in terms of research. That is going pretty well. I have a couple projects on the go and just submitted a proposal or two for upcoming projects, which I'm very excited to talk about once they get rolling and I'm allowed to talk about them, but they will remain secrets for now. And otherwise, I was traveling a bit, especially to Montreal, for a conference on biodiversity. And it was run by an organization that's kind of adjacent to the United Nations, where we're trying to monitor biodiversity the same way that we monitor climate change. So it was a very fascinating and informative conference. And of course, Montreal is a beautiful city. And I think that's the closest I've been to you two for a little while. So it was nice to at least be in the next province to you instead of a few provinces away. But yeah, everything has been busy, but things are going well and research is progressing.
Very good.
So, now just as a quick intro topic, this is a little bit of older news. It was fresh when it was first written down, but I just want to remind you that the Nobel Prizes were awarded within the past about month, and I just want to talk about that. I originally wrote that something that's fresh off the presses. It's not as fresh anymore, but still very interesting. So I want to talk about specifically the Nobel Prizes in physics, chemistry, and medicine, and just briefly explain who was awarded the prize and for what. So the Nobel Prize in Physics was won by Pierre Agostini, Anne Louis and Ferenc Krauts, quote, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter, end quote. So these three physicists separately made discoveries and contributions about the motions of molecules through the production of extremely short pulses of light. And just for reference, an attosecond, of which these pulses were about 250 of at their shortest, comparing 1 attosecond to 1 second is the same as comparing 1 millimeter to about 1 light year. So these are extremely short pulses. And if you want to hear more about very fast laser pulses, you can listen to our episode featuring Dean Eaton, who is currently working under a former Nobel Prize winner, Donna Strickland. So go check out that episode. Now, in chemistry, we had the Nobel Prize awarded to Mungi Bovendi, Louis Brou, and Alexei Akimov for the discovery and synthesis of quantum dots. Now, this is very interesting because the Nobel Prize in Physics and Chemistry could pretty much be interchangeable. They're both relating to kind of chemistry, but also physical components. And in particular, the discovery of the quantum dots were nanoparticles where their size determines their properties, including the wavelengths of light that they emit when excited. So today we actually see quantum dots in technologies such as televisions and monitors, among other things. Now, finally, the Nobel Prize in Physiology and Medicine is shared by Katalin Kariko and Drew Weissman in their development of an effective mRNA vaccine for COVID-19. So they are responsible for the research, and of course, many others are responsible for the research, but they helped lay the foundation for the COVID-19 vaccine and mRNA vaccines more widely. And we now have those vaccines available, and they're being tested for not only new variants of COVID, but also for other types of diseases, whether they're viral, bacterial, or whatnot. So a lot of very exciting and interesting work that went into the Nobel Prizes this year.
It's interesting, actually, because almost immediately after they were announced, it kind of came up in my research a bit. My group, we had a presentation given by a PhD student from the University of Ottawa, if I remember correctly, where somehow it turns out making attosecond pulses is quite hard. But the mechanism that they use to create them, her research somehow sees caustics and catastrophe theory and all that stuff I always talk about in there. It's everywhere, I'm telling you. But there's also another on a different note. There's also some controversy about this Nobel Prize because it was awarded to 3 experimentalists who did various things to make these attosecond pulses realizable. But there was one key theorist who also worked at the University of Ottawa, I believe, who I don't think any of it would have been possible without him. He came up with the theory about how to, not all the theory on its own, but like the big major step about how to create these attosecond pulses. And there's lots of YouTube videos on it, and we should talk about it one day in some more detail. But that guy did not get the Nobel Prize. So there's been some controversy there because they can only award it to 3 people at most, I believe. So the Nobel Prize is great to have, but it's also one of these things where people miss out who should rightfully get recognition. And it's the same thing with these large experimental groups, right? Like sometimes you get someone awarded the Nobel Prize even though they had 100 people working on the project. So they all get it, but only one guy's name or girl's name goes to it.
I know, speaking with Art McDonald once, he said that he sometimes wished, well, to paraphrase, he wished he didn't get the Nobel Prize because everyone thinks that, oh, you've won the top prize. You don't need to get any more prizes. So I know there's a lot of controversy and other topics that would be interesting to discuss around the Nobel Prize.
Well, these days, anything science is, almost always a big collaboration, or it's like a big team working on it, especially cutting edge science. Very little can be done alone these days. Even, your group, the multiple people may be working on the same thing, or a part of the one thing, especially like, let's say Snow Lab with Art McDonald. I mean, it's a huge collaboration. Snow Lab, Snow Plus, there are the dark matter ones, and there are hundreds of people working on hundreds of people working in both sides of theory and experimentation. And to me, it's really hard to really like pick someone, But to pick, if I am to pick someone, I would have to pick, let's say, the lead of the project, or the head of the project, right? Like, it's hard to do. But in terms of theorists who get it, it's also hard to get if it's not realizable by experimentalists. So that's kind of a gray area, which maybe the challenge of realizing it is much more than the challenge coming up with it. But I think that's very debatable. Some could say if you come up with it for the first time, the first guy who come with it, maybe it's so hard because for thousands of years nobody came up with it.
Yeah, there's certainly a lot of, again, interesting aspects of the Nobel Prize and who gets it, who deserves it, who should have deserved it, which I think we'll have to save for another episode, because for now we have to move on. And we are going to do a little bit of a switcheroo just to mix things up for season 5. This isn't a permanent change, but it just happened to be this way for this episode, where we're starting with the story and then ending with the main topic. And we'll figure out where to put how to contact us in there somewhere. But we'll be starting off with the main story, which will give a nice background to our main topic.
Yeah, I think during our, let's call it a practice session, we found out that to discuss this main topic is really difficult because it's based on basically what we were going to say in the story, which is the 3 interpretation of quantum mechanics by Liam. And knowing that before get to the main topic today, which is on like the local hidden variables theory and measurement process a little bit, and basically the foundation of quantum mechanics as we know it and how it comes about. And it's good to get the story straight on, well, what are interpretations that we have in quantum mechanics. So with that, I'm gonna pass the torch to Liam.
Yeah, so it makes a lot more sense. So there's more than 3 interpretations of quantum mechanics, but these are the 3 big ones that I want to talk about. And I wanted to talk about them before Feely got to his main topic that he's going to tell us about, because it kind of sets the stage a bit better. If we just start it with the main topic, people might get way more confused than they need to. So quantum mechanics, we know it's a theory of nature that describes very small things on the atomic and subatomic scales. And we've talked about quantum mechanics many times before. It's a good chunk of modern physics research is related to quantum mechanics. And we know how to use quantum mechanics very good. And by we, I mean humanity. Maybe not me myself. I still struggle with it daily, but humans know how to use it quite well. We understand how to apply the theory behind it, and we have very good experiments to verify how the theory works. However, we still don't have a proper kind of physical understanding of exactly what quantum mechanics even is and how it works in physical reality. Because of this, there's various different theories that describe what the physical nature of quantum mechanics could be, and these are called the different interpretations of quantum mechanics. Although some of them are very, very different from one another, the idea is that they yield all the same mathematics and results that we see in our experiments. So if there was an interpretation of quantum mechanics that didn't match experiments, then it's probably not right. So the idea is that there's different ways to interpret it, but they give you the same thing in the end. However, even though there's different interpretations, despite 100-ish years of intense scientific and philosophical debate, an agreement still hasn't been made on which interpretation is true and what the true nature of quantum mechanics may be. So, out of the three interpretations I'm going to talk about, the first one is called the Copenhagen interpretation. This is one of the oldest interpretations and dates back to the original development of quantum mechanics in the early 1900s. It was primarily founded by Niels Bohr and Werner Heisenberg, whose names you might have heard before. They're two famous physicists. Even though the two had slightly different views on how it worked, they're two of the big founders of this. This interpretation remains probably the most taught and accepted interpretation. It's typically the first one that you get taught as a physics student when you're introduced to quantum mechanics, at least from my experience. I think when we took it, it was the first one they introduced. The other ones we talk about, you might not even get taught in a class. You just hear about online or in papers. And the Copenhagen interpretation has four major components. The first is that it believes that quantum mechanics is intrinsically indeterministic. So that's just a fancy way of saying it's probabilistic. So even though you can perfectly know everything, well, not perfectly know everything, but let's say you have a system, you have a quantum particle, you can't describe how it behaves perfectly like you can in classical mechanics. You can only describe the probability of an event to occur. You can never say with 100% certainty how a particle will evolve or respond to some given stimulus. So, you shoot a magnetic field at a quantum particle. You don't exactly know what it's going to do. You just know what it's probably going to do. The second part is that the Copenhagen interpretation obeys the principle of complementarity, which says that objects have complementary properties which cannot all be observed or measured simultaneously. For example, you can't actually know the precise position and momentum of a quantum particle at the same time due to the famous Heisenberg uncertainty principle. So the more you know about one specific parameter of a quantum particle, imagine its position super well, the less you know about its other parameter, which might be momentum. So you can never know perfectly where a particle is and its speed at the same time. You can only, if you know one really well, you don't know the other. And I think we've talked about this before a few times. These are called canonically conjugate variables that physicists often describe them as. The third component is that the act of observing or measuring a quantum object or particle changes the actual state of the particle itself. So this is related to the famous Schrodinger's cat thought experiment, where the cat is it's kind of like a metaphor for a quantum particle. So you can think of the cat as representing a quantum particle, and the cat's it's in a superposition of two states. It's either dead or alive, and the cat exists, and it actually exists in both states simultaneously according to quantum mechanics. It is very weird when you think about it, which highlights the strange nature of quantum mechanics. Obviously, a cat can't be both dead and alive at the same time, yet quantum particles can be in two states at the same time, according to this interpretation. And once you observe this quantum particle, which is just a fancy way of saying you interact with it in some way, you hit it with a laser or something, the superposition collapses to a single state. So the cat becomes dead or alive and not both. So by looking at or measuring the particle, it becomes a specific state, and you know with certainty it's in that state. And finally, the fourth component is that the Copenhagen interpretation describes quantum mechanics in a way that's independent of a person's mental awareness. So there's a lot of bogus metaphysics out there regarding the nature of physical reality. A lot of people discuss this in forums and other things regarding quantum mechanics. But this last point basically says that consciousness is not something that can influence the physical world. But you'd be surprised how many people think like that, or at least not according to our current theories. It's not. But anyway, so that's the first interpretation, the Copenhagen. The second one I want to talk about is called the de Broglie-Bohm theory, which also has a few other names. It can also be called pilot wave theory or Bohmian mechanics. This theory takes an opposite approach to the Copenhagen one and states that quantum mechanics is actually deterministic, like classical mechanics. So if you happen to know every little detail about your initial quantum particle, in principle, you can perfectly predict what it'll do. You can predict what trajectory it'll follow through space and time. This is nice because it avoids confusing non-classical notions like wave-particle duality and instantaneous wave function collapse and the paradox of Schrodinger's cat, which are all things that the Copenhagen interpretation has. But this theory describes how the properties of quantum particles are modeled by so-called hidden variables, which are these parameters that we can't actually resolve or see them. So in principle, if we could see these hidden variables, we could perfectly predict what a quantum particle could do, but they're called hidden variables. They're so minute, or we can't distinguish them. So in principle, we don't actually know what they are, and therefore we have to use probabilities to describe quantum mechanics. This Bohmian mechanics is also a non-local theory, which I think is going to relate a lot to what Feely will talk about in more detail later. But this is really me just being afraid to talk about it and just leaving it to him, hoping he can comment on it better than I could. And finally, the third interpretation of quantum mechanics I wanted to talk about to kind of set the stage is a bit more of a wild one, and one that maybe more people are actually used to hearing about from movies and things. It's called the many worlds interpretation. And the way I always imagine this is some thought experiment somebody came up with. I don't know who, but imagine that you have a car driving down a road and it comes to a fork in the road. And there's it splits into two. So the car can either continue to drive down the left part of the road or the right part of the road, as the road splits into two different roads. So it can go to the left or right. If you imagine that this car, like Schrodinger's cat, is an analogy for a quantum particle, so imagine this is a quantum car, and you think about what the Copenhagen interpretation would tell you, it tells you that the car would actually go down both roads at the same time. It would be in a superposition of both states, the left road and the right road. And if you were to try and look at the car or measure it, the state would collapse and the car would either move to it would exist in the left or the right road. So that's what the Copenhagen interpretation tells you. But the many worlds interpretation of quantum mechanics is very different, although it has the same outcome. So in the many worlds interpretation, what happens is that the car comes to the fork in the road, and just before it decides to go left or right, two new universes split off from that original universe. So that's kind of wild to think about. In the first universe, the car might go left, and in the second universe, the car might go right. And if you are in your particular universe, if you observe the car, you'll see it in one of the roads, not both. So imagine that the car comes to the road and it turns left. The quantum car, again, comes to the road and goes left. You just happen to end up in the universe where the car goes left, but a almost identical universe is created, except the car went right in that universe. So this is the essence of the many worlds interpretation, is that every possibility creates universes which split off from the original one. So that's kind of wild to think about, and you can imagine how many different possible outcomes there are for every single thing that ever has happened on the Earth, and let alone the whole universe, right? So all of these different decisions or outcomes being made tell you that there's an essentially infinite amount of universes which exist, and there's always new ones being created. Like if I wave my left hand right now, that's one universe. If I wave my right hand, that's another universe, according to the many worlds interpretation. I do one or the other. And it sounds pretty wild, but apparently this interpretation's nice mathematically for reasons I don't fully understand. I know the famous physicist Sean Carroll really likes this interpretation for reasons. And I guess the nice thing about this is that the many worlds interpretation kind of removes the quantum weirdness of the Copenhagen interpretation. Although now you have to deal with the weirdness of infinite universes existing and doing different things. So it's a give and take, I guess. But this interpretation's a bit more popular because you see it in movies and TVs and sci-fi things all the time, like Star Trek. Rick and Morty's a big one. The DC and Marvel universes. There's all these different like simultaneous universes. Into the Spider-Verse with all these different Spider-Mans. They're all universes where slightly different things happened and there were different outcomes. So those are the three big ones. There's other ones as well. One that's gaining popularity is called the quantum information theories interpretation, which I don't really know much about, and I imagine Feely's a big fan of if he were to read into it. But those are topics for another time. So I just wanted to set the stage with these different interpretations. A little a flash lesson.
Well, thank you very much for the lesson and the story, Liam. We'll be getting right into our main topic, which will be led by Feely. But before we do that, I just want to let you know how you can contact us. I figure I'll do this now instead of at the end. So, it's been a while, but if you would like to receive updates, such as what we're doing over long breaks, whether it's cooking a turkey, which again looks delicious, or traveling to a conference, or just posting memes, you can follow us on our social media. We are on Instagram at the Hyperthesis, where we post updates of when we post episodes, as well as updates when we do take breaks, and even updates about why the breaks might be taking so long. Again, we are at the Hyperthesis, and you can send us a DM as well if you have questions, comments, or if you would like to be a guest on our episodes. We're always looking for people who are experts in their fields to be a guest. So if you're interested, send us a DM on Instagram, or you can send us an email. We are hyperthesispodcast@gmail.com. We check it pretty frequently, so you can find us on there. We also have a YouTube channel where you can find, I'm pretty sure, all of our episodes now. So you can watch the very lovely, mesmerizing graphic that Feely has put together and share us a bit more easily. As for listening to us, congratulations on finding us in the first place, but we are on pretty much any podcasting service that exists. I can't think of any that we aren't on. We're on Google Podcast, which will soon become YouTube Music, as well as Apple Podcast. We are on Audible. Just wherever you find us, feel free to share us. Give us a rating or a review if you'd like, or reach out to us however you'd like to let us know if you have suggestions for topics, or if, again, you are an expert in your field and you would like to talk about your field, as long as it's related to science. And now, Feely.
All right. I think this week or this episode, in terms of the material, might be one of the heaviest one because, well, it's pretty hard to wrap your mind around quantum mechanics in general, and this really challenged the foundation or the concept and theories and ideas behind quantum mechanics itself. Is it a good theory? Well, is its description complete? And you will hear names in this, fight or this war, this little conflict that are really similar, familiar, like Einstein, Bohr, and many other ones. So this is gonna be quite interesting.
Yeah, even everything I just talked about, like for me, I've heard it so many times that maybe I flew through it quite fast, and I did that for the sake of time. But I'm sure the first time you hear it makes absolutely no sense. So definitely research this on your own if you're interested in the weirdness of quantum mechanics. Then come back and listen to the episode.
Well, in terms of temporal wise, I think it's quite appropriate because Halloween is coming up on Tuesday, and this episode will be released a few days before. So the two parts that's good. That's perfect for it because we're gonna be touching on a little bit of the spooky action at a distance. I think that's very relevant. And secondly, this is gonna be quite difficult, so it's quite scary for people.
I think almost a year ago exactly, we published an episode on this spooky action at a distance, and we published it as a Halloween episode. So I guess we're just doing the same thing again, but slightly different. I don't know.
Well, the first thing I want to talk about is basically the local hidden variable theory and Bell's theorem or Bell's inequality. So basically, well, the way you want to, well, you describe nature, one thing you could ask it, well, are things local? What it means by that then is that it's everything that can happen only be affected by by themselves and its surrounding. So relativity or general relativity would love that because it says nothing can faster than speed of light. Any interactions at all have to be bounded by speed of light. So let's say time passes 1 second. There's this sphere of the distance that light can travel in 1 second around a point that is causally possible. So anything outside that cannot be affected by event that's inside that bubble. So it's basically locality. So everything is local. However, quantum mechanics kind of allow, in fact, from quantum entanglement. So it seems that things can be instantaneous. That when you change something far away, you can instantly change something that further than or faster than speed of light. So instantaneous, and that is a big paradox that people. Well, I think even for now, people are still debating about it, determinism, or even if things are truly indeterministic, or there's no randomness, or everything is deterministic, or is there actually a hidden variable that we don't know about because things are deterministic? We just don't know about some variables that make these things that we don't understand. Or are there things that truly random? Or you can expand those arguments that argue on realism, that do things exist if we don't? All right, that do we require observers for things to exist, or things exist independently of observers?
So coming back to the whole non-local thing in quantum mechanics, I mean, I know we learned about this, but how does that work? I know how it works, but I'm trying to get you to say it. What is that? There's that thought experiment with the mittens and the boxes, and how you can know information faster than the speed of light. So you can, at first glance at least, you can break locality, right?
Well, I think if you want to go that far, sure. So so for the mittens in a box, so let's say you have a pair of mittens. It's definitely you have left hand and right hand, right? So now if you don't see, when I have two boxes and I put one in each, I don't tell you which one I have, right? And I give one to you, and I take one, and I go I give the other one to another guy, to Patrick, and I separate you guys to go very, very far apart, right? So if you open the box, if it's left-handed, you know right away that Patrick has a right-handed one. So it seems like when you opening the box, it's not 50-50 anymore. It's 100%. So So does it mean that Patrick instantaneously have the right one. Or the realism argument is like, well, it doesn't matter because it's already left or right, whether you know it or not. So knowing doesn't do anything. But because there's this hidden variable that we don't know, that actually everything is deterministic. However, the way you solve it in relativity is that, well, you might know that he has the right-handed one, but he doesn't. So Patrick doesn't. So it takes time to transmit that information, and that transmission it's bounded by the speed of light. So in a way, even though you know, but he doesn't know. So to make everybody knows, it's still bounded by the speed of light, by causality through light.
Yeah, Patrick flies across the universe in his spaceship, and you open your box, and it's a left mitten, even though you instantly know Patrick is a right mitten. If you tried to send him a mess, like a radio message, or whatever, it would be bounded by the speed of light. It couldn't reach him instantaneously, and this is something we've definitely talked about before. And relating to quantum mechanics, in quantum mechanics, you don't have mittens; you have what are called entangled particles. So you have two particles, you separate them really far, and they're entangled in the sense that if you measure one of them and it ends up in some state, you immediately know what state the other particle's in. I just wanted to this is all a lot of words and it's complicated, so I kind of wanted to ground it a bit.
Yeah, I think Bell's inequality is a more rigorous version of that, right? So basically, instead of doing it once, you did multiple times over the multiple possible state outcomes. So one thing I want to talk about is the Bell's inequality. That there was this idea that the quantum mechanic is incomplete and have local hidden variables, so that we don't know. That's why we call it hidden. So if you can set up the experiment with pair states, or even more than pairs, but for simplicity, we say pair state, like mittens, right? Left and right. Let's say electron pair. It can either be up or down, electron spin. And if you measure a bunch of them that are paired, the simple version is that there are, if for everything that happened locally, there are an upper bound limit on the probability of finding specific outcome that always under this inequality. We call this Bell's inequality. So if we measure multiple times and draw correlation, it shouldn't be more than specific percentage, for example. However, if things can affect at a distance, or if that interpretation of mechanics is kind of sensible, we would find correlation that you can measure that breaks that basically more than the inequality allow. So basically, people actually do this many times. That's why people start to say that local hidden variables are impossible. Wishbone mechanic, or the second interpretation that Liam talked about, challenged that heavily. In fact, it was John Stuart Bell himself that's a main proponent of Bohmian mechanics, and which is interesting because people would say, he came up with a way to invalidate determinism of hidden local variables, but it's him that a main proponent of this locality, that he said, when you do that, you kind of misapply the inequality. So this is kind of something that I will touch on. So there is this spooky action, which are basically at a distance that seemingly instantaneously affect all the particle. So, well, maybe that's true because a lot of experiments kind of point that way. And however, remember, this is a statistical theory, right? So you count multiple things and you perform statistical stuff on it. But when is this one thing? It might be different. That's the same reason I say, well, people say that principle of macroeconomics, well, it makes sense when you look at people. When you look at each individual decision, macroeconomics doesn't make much sense but microeconomics starts to come in the same way when you have to be careful when you use statistics. However, so one thing that this inequality or Bell were working on was really criticized, or even before that, this idea of locality was challenged by this, we call it the EPR paradox. So EPR are three people: Albert Einstein, Boris Podolsky, and Nathan Rosen. And these three came up with the idea to challenge the quantum mechanics. At the time, quantum mechanics were pretty new, right? There's the new ideas, new concept, and it's quite radical because it's challenged determinism. So before deterministic things, let's say this equation describes exactly the reality, and there's no randomness. If I throw the ball one way, a specific way, it will land at this place every time. And quantum mechanics introduced this idea of randomness or stochasticity.
Yeah, I just want to comment that a lot of the people who founded quantum mechanics did not like it at all because of how weird and funny it was and how little intuitive sense it made. So a lot of like the EPR paradox, a lot of people who, like Einstein was one of the founders of quantum mechanics, he tried to break it as much as he could. He's famous for saying God doesn't play dice. He was not a quantum mechanics enthusiast, although you can't argue with the experiments.
I will also say it took a long time to catch on. Nowadays, it's taught in undergraduate degrees, but if you've seen the movie Oppenheimer, for example, Oppenheimer was one of the first people to actually take quantum mechanics to the North American continent. Like it really took a while to really grab on and grab hold of physics in general. Like it's widely accepted now, but even then, there's a lot of questions with it.
Well, I think Liam, even though you say you can't argue with experiments, that was Bell was trying to do, because he basically claimed that experiment was set up wrong or misapplied the way that should work. But I'll talk that soon. So basically, without explaining the actual paradox, the paradox really boils down to two things. So it really gives you two choices. One is either, so the description of reality given by the wave function in quantum mechanics is incomplete, or two, quantum operators cannot have simultaneous reality. So let me explain that. So the first one, what do you mean by quantum mechanics or the wave function is incomplete? So what it basically does is that the description using wave function, which is basically, when you do quantum mechanics, that probably the most important equation you learn, which is the Schrodinger's equation. And the Schrodinger's equation describe how wave function, which is basically the main variable, evolve through time and space, and how measurement work. Because instead of having particles or having a wave, we have something called wave function that's not particle, not wave, but this quantity describe describe the evolution or describe a state of a system. The system can be a particle, can be wave, can be atoms, can be electrons, can be protons.
Yeah, you think of like waves in the ocean, right? Those are waves described by some equation called a wave equation. In quantum mechanics, these quantum particles are described by probability waves. So the wave function, it's a wave equation like how water waves are, but it describes probabilities, not actual physical waves.
Well, wave function have to be a little precise, because wave function does not describe probability. The norm of the wave function is probability, but not the wave function itself. It's strange when you think people are more used to, let's say, the Gaussian distribution, right? That's like a probability distribution. You can draw the bell curve, and those are distribution that describe probability. Wave function is not that. It's less. It's easier to think as something that could turn into that. It's a strange little thing.
Yeah, wave functions are in general complex
Mhm.
valued functions, so
Yeah.
they're not real. But when you take their modulus squared for the physicists out there, you'll know what we mean. But
Well, yeah. So what really Einstein or the EPR claims that or is either that wave function cannot describe the entire reality, so it's incomplete because maybe there are hidden variables somewhere that are not part of the wave function, so you cannot describe everything completely, or the two quantum operators cannot have simultaneous reality. The way to understand this statement is kind of tricky. The way I do it is that what are quantum operators? Right? Quantum operators are the mathematical object that operates on the wave function, and it can do many things. Oh, and operates with according to Schrodinger's equation too. It can do many things. It can give you a measurement, or it can evolve or change the wave function. So the way it kind of described in a paradox is that, well, if it's gonna break relativity, it would have to measure the thing, measure your system, and transmit information at the same time. If you do that, you can break this causality set by general relativity. So you can. So they say, well, you cannot do that. So what they propose is basically, well, what people propose is that measurement and transmission cannot happen at the same time. So, like, let's say if I open the box of the mitten box, I can't open it and tell Patrick at the same time, right? I have to choose to open it first and then perform this second operation called transmission to let other people know. So measurement is not observation. Oh, okay. Measurement and transmission are distinct and have to be a distinct quantum operators. So, um, so this type of hidden variable approach that has this implication that if there are hidden variables, all the quantum state is already determined previously. So all that's left is to measure the state. We just don't know the hidden variables. It's already there. There's no probability really. So it's really just deterministic. Everything is deterministic. We just don't know what's hiding under the rug that make it that way. And that's an entertaining idea and a really profound idea that everything is there. So it's kind of support this realism that no matter what you observe or not, it does not matter. It's there. It's following this evolution by rules and laws and theories and equations by Schrodinger's equation. So that's one of them.
yeah, and that description, it makes a lot more intuitive sense. So back when quantum mechanics was new, most of the physics that physicists did was all, classical mechanics. So everything was deterministic. If you have a ball and you know its position and momentum, you know what its exact trajectory will be, um, based on whatever system it's in. So you throw a ball, if you know its initial position and velocity, you know where it's going to go. You know where it's going to land. So a lot of physicists, they were trying to take quantum mechanics and say, is there some way we can make this easy to understand? And this hidden variable theory, the second interpretation I talked about, that was the best. That was one of the ways people thought. They thought maybe there's these, like you just said, there's these hidden variables, and in that way, all this quantum weirdness goes away, and it's just our lack of knowledge that makes it seem random.
Yes, and actually, I'm getting to that next. So the Broglie, who basically came up with the first when he basically started this hidden variable theory into the description. Unfortunately, I think at the time this Copenhagen interpretation becomes bigger and bigger, and everyone's kind of support this Bell inequality and Bell theorem, and kind of kicked away this determinism. So he kind of gave up on it. But David Bohm, Bohm, David Bohm, he basically picked up the idea and really formalized it into this Bohmian mechanics, and it's wonderful. So let me get into that a little bit. So some people call it the pilot wave theory. The idea is that there is something called spatial probability current associated with the wave function and its evolution. So, and that is basically the basis of Bohmian motion. That's so what it's basically doing before. So Bohm basically formalized a way to put something that hidden and integrate it into something deterministic. So I'm gonna try to explain this kind of. How should I explain it? Basically, if you want to make some theory that are deterministic, you shouldn't have some hidden variables that seemingly random. So the way Bohm derived the Bohmian mechanics, he basically have this hidden variables, and you can kind of put it influence into the equation rigorously, and that is enough to describe what's going on in Bohmian mechanics, in quantum mechanics, basically. They basically support this. Okay, I'm gonna basically put the quote by Bell. He kind of commend Bohm that show this because that's what they believed in. So I paraphrase this to say, it was in the papers by David Bohm that show explicitly how parameters could indeed be introduced into non-relativistic wave mechanics with the help of which the indeterministic description could be transformed into a deterministic one. So this description of the indeterministic of randomness can be transformed into something that deterministic. And in his opinion, that this subjectivity of orthodox version, this reference to observer can now be eliminated. You don't even need observer for Bohmian mechanics. So there's no need for observer to collapse that wave function. You can transform using parameters to transform this unknown hidden variables into a deterministic theory. That is why it's kind of one of the beautiful thing about Bohmian mechanics. And Bell has actually said this, and I quote, to show us that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice. That I think that is powerful. Like maybe because it's set in that way by this bias that things are not deterministic, it's actually a choice of theory that put it that way so that the experiment verify those. So maybe people might disagree with that, and it is a something quite difficult. And so right now I'm not really sure which to believe is Bohmian mechanics are quite nice, and having deterministic things is quite preferable because we know exactly what it's gonna be. We know the state and evolution.
Yeah, like you can't have two. Like obviously, it's different because cats are macroscopic objects, but intuitively, you can't have a cat that's both dead and alive, right? So it's weird that a particle can be in two states at once. So I always get confused about this thing with Bell's inequality. So where does Bell's inequality come into Bohmian mechanics again? So Bell's inequality, certain quantum mechanical states violate it, which means that you can't have a local hidden variable theory. So can you connect that to
Okay.
Bohmian mechanics? Because I always I never fully understood it really.
Well, I think the way Bell would see it is that, well, it doesn't say that it's impossible. Is that what most people would say? Well, because it breaks the inequality, it means local hidden variable is impossible. No, it doesn't say that it's impossible. It just says it allows action at a distance. It doesn't mean there's no local variables. And that's one way to look at it, I think. Because let's say, so if things can happen only locally, right? All the statistical things which show this correlation, which is upper bounded by a number. However, if things can affect others instantaneously, the correlation you will get, it will be more than that upper limit. So basically, it's like something is interfering it from outside the local instead of everything have these hidden local variables. So people will say, oh, then local hidden variable is not possible. Well, but that's not what it does. What it does is just saying that spooky action at a distance is possible. It doesn't say that there's no local hidden variable. It could still be local hidden variable and spooky action. Or unless I think of it wrong.
Yeah, it's really, I mean, people still don't really understand it, right? So it's not something we have an actual answer to.
So one of the person that I saw recently in the video on this website that is a huge video distribution platform called YouTube. So it's a video of Roger Penrose, our very own, our very own Penrose that does many things, but he has really interesting take on it. So he was asked about the inconsistency of quantum mechanics, and I'm going to quote him here, and I quote, the way physicists usually use the Schrödinger equation is to work out certain probabilities of what an observation on the system would tell you, so that what you have to do is wheel out of the cupboard a measuring device. In this measuring device, you set it on the system, which is evolving according to the Schrödinger equation, and it measures. The process of measurement does not follow the Schrödinger's equation. It gives you a probabilistic answer, this or this or this. That's another outside the system problem. That's certainly outside the Schrödinger equation. And end quote. Basically, Schrödinger equation tells you how the system evolves when you measure it, but it doesn't tell you what constitutes a measurement. Which is interesting, isn't it? Schrödinger equation doesn't tell you what is the nature of measurement or what is a measurement. They said, hey, here's some operators collapse the wave function, whatever that means. And we describe it very well of how state evolved, but it doesn't tell you what is the nature of that measurement. Does it mean like for Schrödinger's cat or the mitten in the box, it's opening the box, the measurement? How do you open the box? You have to open it fast? Do you have what rules you have to follow for it to be a measurement?
Yep, it's it's very cool stuff. It's very wild to think about, and it's very like the Schrödinger equation's non-relativistic, right? You have to start doing quantum field theory if you want to include relativity, which is a whole other topic and a whole other theory. So it's always interesting to talk about Bell's inequality and locality and all this stuff. But the moment you start dealing with things like spooky action at a distance, you kind of have to now take into account relativity. You can't just use Schrödinger equations. You have to kind of upgrade. So I know Bohmian mechanics. I know the Copenhagen. Well, I don't want to get into quantum field theory too much, but I know Bohmian mechanics, people have struggled to integrate it with relativity a bit because of this whole non-locality thing. But that's probably, for the sake of time, we should wrap things up probably.
Well, one thing I want to talk about is Penrose also talk about his conversation with Wigner. He's old enough to be able to talk to Wigner in person, right? And Wigner believe maybe he claims that it's not as dogmatically, but he believed that a measurement requires a conscious being, and that is a very hot take, right? It is a very hot take that consciousness actually collapse the wave function, which to me doesn't make that much sense because things exist before we exist, before consciousness exists, but also, there might be claimed that there are other types of consciousness of higher beings, but
Yeah, I think there's a lot of thought experiments and evidence to disprove that. Wigner was a wonderful physicist, but I don't think he got that right, in my opinion. I mean, he's obviously smarter than I was, but.
Well, with that little nugget of thought to think about, like, do we need consciousness for all of that? Feely, any kind of last words on this main topic?
Yeah, I think I'm gonna leave you with two keywords, and the first one is realism. So I want people to think about it. that realism is the idea that nature or things exist independently of whether somebody is witnessing it or not. And that is one thing that quantum mechanics challenge, or it challenge you to think about it. Do things really exist if you don't measure it? And let's say Copenhagen interpretation would tell you, oh, it doesn't. It's just probability. You don't know. Then the Bohmian or maybe other one said, well, it does. It always does. And it looks like probability or possibilities because you don't know. There's some hidden variables behind it controlling it that you don't know. So it seems random, apparently or ostensibly random. So I think that's one first thing I want you to keep in mind in this episode. And the second thing is locality. So it's this principle that an image is directly influenced only by its immediate surrounding. So no information or cause can be transmitted faster than the speed of light. So I want you to have this concept of locality, what it means, or to understand that there's this bound by speed of light, that things can only be affected by that, and that causality is bounded by speed of light. So that is two nuggets to think about if you haven't got too much. Is a lot of these, what we say, escapes you. So I think this is the end of the episode. I will wrap it up here. I hope everyone have a good night and take care.
Bye, everyone.
See ya. Thanks for tuning in for our first episode of season 5. Yeehaw.